Hi everyone.
So
Now
in
we are at
this
unit number 2,
session, I'm going to
lection
discuss
number
about
14.
reduction of quadratic form to canonical form. Okay, so we are finding the canonical form from where we are obtaining from quadratic form only through the mediator orthogonal transformation. So by using orthogonal transformation, we are finding canonical form from quadratic form. Okay. So before entering into canonical form in this process, let us know about what is meant by orthogonal transformation and what is meant by some normalized vectors. Okay. So these two things we have to discuss first. Normalized vector, this one, and second one is orthogonal transformation. So now let us quickly recall. Normalized vector. You know already this normalized vector from physics. So let V is a vector. Let us take 3 by 1 vector, 3 rows and 1 column. You can take 4 by 1, whatever. One column vector I have taken, general column vector. Then its normalized vector is defined like this. So each and every component is dividing with its length of this vector. What is the length of this vector? Square root of x1 square plus x2 square plus x3 square. That is the length of this vector, right? Norm of the vector, norm V. So we are dividing with the norm. So this vector is said to be, this is called normalized vector of the vector V. Okay, so that's what indirectly by dividing each component of V by its length, square root over x1 square plus x2 square plus x3 square, then you get normalized vector of V, such that the length of the normalized vector is 1. Norm V is 1. So this is about normalized vector. And second one is orthogonal transformation. So a linear transformation T from V to V, which preserves lengths of vectors and angles between vectors. So what is meant by this? Preserves lengths of vectors and angles between vectors. Its meaning is, for example, look at let us take two vectors. The two vectors are, assume this is v1 and this is v2. Okay. This is v1 bar, and this is v2 bar. Okay, two vectors I have taken. So now the angle between these two vectors is some theta. Let's call this is some theta. Okay, so this is before transforming. Before transforming, two vectors v1 bar and v2 bar I have taken. After transforming through the transformation t here, so this transformation, look at t from v2 through this transformation, what I have to get is, look at this kind of vectors I am getting. I am transforming like, or by some through some matrices or with some multipliers, whatever. Just I'm transforming that vectors. Now I'm getting this kind of vectors, like I'm getting like this. Let us call the vectors are like this. Okay. Now this is transformed. So let us call this vector some u1 bar, and this is u2 bar. Okay. These are after transform. So v1 bar is converted like u1 bar, and v2 bar is converted like u2 bar. Now angle between these two is some theta. So angle is not changing. Look at, for example, initially the angle between v1 and v2 bar is some theta. Let's say some 45 degrees. After transforming the two vectors, also we'll get again the angle between these two vectors is theta only. So angle is not changing. Similarly, length of v1 must be equal to length of u1, and length of v2 must be equal to length of u2. If such a thing is happening, then that is called preserving lengths of vectors and angles between vectors. Preserving means not changing the lengths before transforming and after transforming. And similarly, angle is also, angle between the two vectors is not changing. That is called preserving lengths and angles. Such a transformation is said to be orthogonal transformation. Okay, I am transforming the vector y2. Now it is going to p of I. Now domain vector is y, codomain vector is p into y. So now y is transforming as p into y. So now this one I can write as some, you can call like this one as some x is equal to py. Let us call like this. Okay, now x is x means t of y. This entire value I am calling some x. So x is equal to p of y. So now y is a old vector, y is a domain vector. Now p into y, that means x is a codomain vector. Okay, so y is domain vector, y is domain vector. Okay, and p into y is codomain vector, codomain vector, like this. So like this the vectors are transforming such that it preserves angles between the two vectors, and it preserves the lengths also. Okay, so particularly for this transformation and for this matrix and for this inputs, two vectors v1 bar and v2 bar. Now let us find out how it goes on. So now since transformation of the vector, first vector I am taking, so 1 0. Okay, now 1 0 is like y. Now y is 1 0. Okay, now how it transforms p into y. So p into, what is p now? So p into y. Now what is y now? 1 0 1. Okay, now what is p now? P is nothing but cos theta minus sin theta and sin theta cos theta. Okay, into 1 0. Now what will you get? This is nothing but cos theta into 1 cos theta minus sin theta into 0 0. So cos theta and sin theta, yes, sin theta plus 0. So you will get, so this is 2 by 2 matrix, 2 by 2 matrix, and this is 2 by 1 matrix. What is the resultant matrix? 2 by 1, right? So yeah, sorry. So this will be, so first summation, let me write like this so that it will be very clear. So what is this? Cos theta into 1 cos theta minus sin theta into 0 0. So cos theta plus 0 you write like this. It will be very clear. Cos theta plus 0, and sin theta into 1 is sin theta, and cos theta into 0 is 0 plus 0. So finally you will get cos theta and sin theta. Now look at how it preserves. What is the length of this vector? See here, what I am taking is, let v1 bar, so let v1 bar is 1 0. I am taking 1 0. Okay, now what is the length of this vector? Now what is the length? Norm v1, norm v1, length of the vector is square root of 1 square plus 0 square. How much it is? Just 1 only, right? Now look at this one. Now this is a resultant one, right? This 1 comma 0 is domain vector. Codomain vector is this one. Now what is the length of this vector? So this is like p into y, right? P into y. So what is p into y here? So length of p into y, p into v1 bar, let us take. Y means here v1 bar. Okay, now what is that length? What is the length of this? Cos square theta plus sin square theta. Now what is this? It is 1. Look at, length is not changing. Similarly, if you send one more 0 and 1, its length is 1. Again we will get what will you get? 0 and sin theta and cos theta will get. Again sin square theta plus cos square theta is 1. Length is same, and you find out the angle between them. So 1 0 0 1 means, so 1 0 will be here and 0 1 will be here. So what? So this is the one first vector. This is the second vector. What is the angle? 90 degrees, right? Similarly, you take, this is first vector, cos theta and sin theta is first vector. Next you find out second vector and find the angle between them. The angle between them is also 90 degrees only. So such kind of transformations is said to be orthogonal transformation. So let me find out that vector also. So t of 0 and 1. Okay, so now this is p into 0 1. Okay, this is equivalent to, so now cos theta minus sin theta and sin theta cos theta. So 2 by 2 matrix, cos theta and sin theta. Okay, and the vector is, input vector is 0 1. Now what is the resultant vector? Minus sin theta, isn't it? Cos theta plus 0, cos theta into 0 0 minus sin theta into 1 is sin theta, and this is cos theta. Okay, so now again same story. So assume this is v2 bar. So let v2 bar is, some 0 and 1. So this is v2 bar. Okay, then proceed same like this. Such kind of transformation said to be orthogonal transformation. This is just for understanding only. So by using these kind of transformations, we are going to find the canonical form from the quadratic form. Okay, now let us come to the canonical form. So in general, so let You take first quadratic form, let x transpose A into x be a quadratic form. Okay, quadratic form. Quadratic. Then let t from V to V be a linear transformation. Okay, and I have to use a transformation. What kind of transformation I am using is, just now we discussed already. So t of some A, look at this, go back, t of y is going to p into y, right? Same like that. So t of y is mapping to p into y. Okay, so now I want to use a different one. Instead of p, I'm using n. So same only, but I want to use this transformation. T of y is equal to some n into y. Again, same, n is orthogonal matrix. N is orthogonal. Why I'm using n, I will tell you. N is orthogonal matrix. Okay, so now let us transform. So now old quadratic form is x transpose ax. So by using this transformation, what I'm doing, I am converting into another form that is called canonical form. Okay, x transpose into a into x. Now this how it is modifying, look at. So let us call this t of y is equal to some x. Okay, so x is equal to n into y. So instead of x, let us substitute this. So n into y whole transpose into a into x, n into y, n into y. Let us modify this. What will you get? Y transpose into n transpose, right? By using properties of transpose, y will come first. Y transpose into n transpose into a into n into y. Now look at this one. N transpose into a into n, I am calling this one as some matrix D. So now y transpose some matrix D into y. Again look at the same form only. Okay, transpose D into y. So we need to convert into this format first. Okay, then this is called canonical form. Canonical form. What is the importance of this canonical form? I will let you know soon. But before that, let us know what is meant by canonical form and how to find canonical form from the given quadratic form. So this is about canonical form. Let us know about the definition, formal definition. Canonical form. The quadratic form x transpose ax can be reduced to the quadratic form y transpose d into y. Look at y transpose into d into y like this. But it is given as lambda I into yi squares. Since I am using y, so therefore what is x here? Actually x means it is a column vector, right? Here x is some column vector. Let us, for example, 2 by 1, let us call x1 x2 like this. It is a column vector. So if I take y is a column vector, therefore it must be y1 y2 like that. So that's why I'm taking here yi squares like that. Okay, and lambdas are nothing but eigenvalues. So we will know this, don't worry about this why lambdas have come, but just remember the canonical form is y transpose d into y. This is enough. So this is a canonical form of x transpose ax through orthogonal transformation. X is equal to n into y. Look at x is equal to n into y. This transformation I am using. Okay, where n is orthogonal matrix. Where n is orthogonal matrix, so that determinant of n is 1. Then y transpose d into y is called the canonical form of the given quadratic form. Clear? When you enter into the problem, you will get to know this very clearly. But this is a fundamental idea about canonical form from the quadratic form. So now let us do one problem. Problem number 1. Find the canonical form of a quadratic form. This is a quadratic form by using an orthogonal transformation. Hence find nature, rank, index and signature of the canonical form. So first let us find what is canonical form. After that we will get into know all these things. Okay, through orthogonal transformation we need to find. So first, yeah, let us find the canonical form. Okay. Yeah. So according to the phenomena, first what I want is a transformation x is equal to n into y, right? X is equal to n into y. So x is a old vector and this is a what is this orthogonal matrix, and this is a new vector column vector y1 y2, and this is x1 x2 column vectors. Okay, so here what are the unknowns? This we know already column vector, this we know this is a column vector, but this is unknown, right? N. First we need to find what is this, what is n, before entering into this orthogonal transformation. So now I am going to find what is the matrix n. Once n is known, then after that what I will do, once n is known, then look at, go back. Once n is known, look at here, if the matrix n is known, what I will do, I will modify this quadratic form through this transformation. So n transpose I will calculate. A already given. What is A? A can be obtained through the quadratic form. So A will be known, and n matrix I am computing already. Then I will compute what is this value. Product of these three matrices, I will get matrix D. So once D is obtained, then problem is over. I will multiply y transpose into D into y. That's it. This is my canonical form. So our main goal is what is n. Once n is known, then I will compute this value. This value is nothing but D. Then once obtained D, then I will find this one. This is nothing but canonical form. Clear? Now let us do this. Yeah, our main goal is to find what is n. Okay, so before that, so the quadratic form is, so q of, how many variables are there? X, y, z, three variables. So x comma y comma z. So three variable, x square plus 2y square plus z square minus 2x into y plus twicely y into z. Now the corresponding matrix associated with this quadratic form. So therefore let us call that matrix is A. Okay, yeah, you know already. Yes, x square means a11. What is the x square coefficient? 1. So a11 is 1, and y square coefficient is 2. So a22 is 2, and a33 is 1 over 1 to 1 over. Next, see x, y, z three variables. If you call x is first variable, y is second variable, z is three variable like this. Then x into y means 1 2 1 2. That means a12, a12, a21. So a12 plus a21. The sum is how much? Minus 2, because its coefficient is minus 2. So this is a12 and this is a21, right? So therefore this sum is minus 2. Therefore I will assign this is minus 1, this is minus 1. If you do addition, you will get minus 2. Remember, I am finding symmetric matrix. Symmetric matrix is unique. So many matrices exist, but symmetric matrix is unique. Next, y into z. Y into z means what? 2 3. 2 3 means here a23 plus a32. That means y into z coefficient. Y into z coefficient is 2. So y into z. So yeah, a23. This one is a23 and this one is a32. So this sum is how much? 2. So therefore this is 1 and this is 1 over. Okay, next one, these two are left. What is this? a11, a12, a13. 13 means what? X into z. X into z is here is option, therefore 0, and y into z also 0, therefore this is 0 over. So this is a associated matrix of this quadratic form. Once A is obtained, then find out what are the eigenvalues of this matrix A. Okay, first compute eigenvalues. I am telling you how to find n. N is orthogonal matrix. How to construct orthogonal matrix such that, see, whatever orthogonal matrix you should not take. particular orthogonal matrix only you have to take. Why? Because here, what is meant by orthogonal transformation? It should preserve length of the vectors and angles between the vectors. Such kind of orthogonal matrix only you have to take. Such kind of orthogonal matrix will change problem to problem. For this particular problem, one orthogonal matrix exists. If you change these coefficients, another orthogonal matrix exists. So orthogonal matrix is not unique, it will change problem to problem. Okay, how to find such kind of orthogonal matrix? Let us look at. First, let us know eigenvalues of this matrix. Okay, now eigenvalues. So characteristic equation A minus lambda I equal to 0. That means matrix A you write. So determinant of 1 minus 1 0 minus 1 2 1 and 0 1 1. This is matrix A. A minus lambda into I, identity matrix. 3 by 3, 1 0 0 0 1 0 and 0 0 1. This is 3 by 3 identity matrix. Then determinant equal to 0. So solve this. So try this, you will get the eigenvalues directly I am writing. So eigenvalues are 0 1 3. Take it exercise. Okay, so try this. Eigenvalues are 0 1 3. Okay, so after knowing the eigenvalues, then find the corresponding eigenvectors. So let us compute what are the eigenvectors. Okay, eigenvectors. So first with respect to the eigenvalue, first with respect to the eigenvalue, lambda is equal to lambda 1 is equal to 0. Okay, so with respect to this, what is a eigenvector? How to find eigenvector, you know already. So A minus lambda I into x equal to 0, null vector, not 0, null matrix. So such kind of x we need to compute. Here x is unknown. Okay, here lambda is 0. Then plug in back. So the matrix A is 1 minus 3 by 1 matrix, 3 rows and 1 column. So you have to solve it. Okay, now so this 0 into this will be 0 and only this matrix will left. So what is that? So 1 minus 1 0. So 1 minus 1 0, right? Next 1 minus 1 0 minus 1 2 1, minus 1 2 1, minus 1 2 1 and 0 1 1. Okay. To x1 x2 x3, okay, equal to 0 0 0. See, no need to apply Gauss-Jordan elimination method. So directly you construct the equations. What you will get? So therefore from here, so x1 minus x2 equal to 0. Multiply this, 1 into x1 x1 minus 1 into x2 minus x2, 0 into x3 0 is equal to this first 0. Similarly, second equation, minus x1 plus 2x2, okay, plus x3 equal to 0. And third equation, x2 plus x3 equal to 0. And assume this is equation number 1 and this is number 2 and this is number 3. Okay, so now let us take equation number 1 and 2. So what I am doing is 1 plus 2 I am doing first. Okay, 1 plus 2. What I will get? 1 plus 2. So first equation plus second equation I am clubbing, first and second equations. So x1 minus x1 0. So minus x2 plus 2x2. So just x2 only, right? 1 times x2 plus x3 is equal to 0, and this is equation number 4, new equation. Okay, now look at equation number 3 and 4. They are in terms of x2 and x3 only. Now let us solve these 3 and 4. Solve 3 and 4, 3 and 4, so that you will get 1 variable value, two variables values will get. Okay, so indirectly these two are same, right? 3 and 4 are same, therefore let us take any of the equation. So therefore let us take, so therefore x2 plus x3 is equal to 0. So from this, what is x2? x2 is equal to minus x3. Okay, x2 is minus x3. Assume this is number 5. Okay, and let us take equation number 2. Equation number 2 implies, so equation number 2 implies, what is 2? Minus x1 plus 2x2 plus x3 is equal to 0. So from this x2 value, how much? Minus x3. So therefore let us plug in back. So minus x1, okay, minus x2 value is minus x3, so minus 2x3 plus x3 equal to 0, since by using equation number 5, since by equation number 5. If you don't want to do all these things, just apply Gauss-Jordan elimination technique, your wish. So now this is minus x1 and minus x3 equal to 0. So from this again, what is x1 now? x1 is nothing but minus x3. Okay, look at equation number 5 and 6. x2 is minus x3 and x1 is minus x3. Therefore, let us call x3 is some k. Okay, so let x3 is equal to some k which is belongs to non-zero real number. Okay, so once x3 is equal to k, so therefore what is x1 now? x1 is equal to, so this is from 6 implies x1 is minus x3, so minus k. Okay. Next equation number 5 implies, what is x2 value? x2 value is also minus k. So therefore the solution is, so therefore x eigenvector, let us call this eigenvector as some x1. So x1, x2, x3. Okay, first eigenvector through the first eigenvalue 0. Okay, what is x1 now? Minus k. x2 is also minus k. What is x3? x3 is k. Okay, if you take k is out, we'll get minus 1, 1, 1. Okay, so this is about the eigenvalue with respect to 0. This is the eigenvector. Okay, now from here let us take some value of k. What is k here? K belongs to r minus 0. Why minus 0? I told you already. Once I am telling you, if k is equal to 0, what happens? 0, then 0 into this is 0 only, so null vector will get. But x1 is eigenvector. Eigenvectors are non-zero vectors. That's why k should not be equal to 0. That's why k coming from r minus 0. I hope it is very clear. So next one, so let us find the particular eigenvector. So let us choose, so let whatever the number of for k you choose, you can choose 1, minus 1, 2, whatever you can choose. So I'm choosing k is minus 1 for particularly. If k is minus 1, then what is x1 now? Particularly x1, one eigenvector I want. Okay, linearly independent vectors I'm generating now. Okay, so for minus 1 it will be 1, 1, minus 1. Okay, one eigenvector is over. Next, two more eigenvectors I need to generate. Okay, so now with respect to the eigenvalue, lambda 2 is equal to, what is second eigenvalue? So 0, 1, 3 are the eigenvalues. With 0 is over. Next, let us take eigenvalue 1. With respect to 1, what is the eigenvector? Now let us compare again same story. A minus lambda into I into x equal to null matrix. So 0, 0, 0. Yeah. Now let's simplify this. What will you get? So L minus 1 minus 1, 0, first entry. Okay, next minus 1, 0. Only diagonal entries are reduced with 1, reduced by 1. So 2 minus 1, 1, 1, and 0, 1, 0. Okay, into x1, x2, x3 equal to 0, 0, 0. Right? Next one. See, let us club row 1 and row 2 and write here so that this becomes 0, or directly write the equations. Directly minus x2 is equal to 0, right? Next step, minus x2 is equal to 0. So minus x2 equal to 0. Next one. So x2 is 0 overall, so therefore x2 equal to 0. And from this if x2 is equal to 0, so minus x1 plus 0 plus x3, isn't it, is equal to 0. So therefore what is x1 value? X1 value is minus x3. So therefore let x1 is equal to some x1 or x3, whatever, x3, let us call x3. X3 is equal to some k. K belongs to real number system, non-zero real number. Okay. Now what is eigenvector? So therefore second eigenvector I am generating, second eigenvector, which is x1, x2, x3. Okay. And substitute back all x1, x2, x3. What is x1 value? X1 value is minus x3, but x3 is equal to k. Okay. So let me write here. So therefore once x3 is equal to k, so therefore let me write here, therefore x1 is minus k. Okay, so let me write here, so x1 value minus k and x2 value 0 and x3 value I am assuming k, right? So x3 is k. So now this will be k will out, what will you get? Minus 1, right? 0 and 1, minus 1, 0 and 1. Okay, so this is, I think, yeah. So here it is not minus, right? Let me, so this will be x1 is equal to x3 only, right? Because x1 is equal to minus x1 is equal to minus x3, minus cancelled, x1 is equal to x3. If x3 is equal to k, so therefore x1 is equal to k. So therefore it is minus, so plus, not minus. Yeah, because single minus will change entire problem. You know already. So for k value, so let k is equal to some whatever. For simplicity, I am choosing 1. For k is equal to 1, so therefore what is second eigenvector x2? Now x2 become, substitute k is 1 here, we will get 1, 0, 1. So this is second eigenvector which is linearly independent to x1. Okay. Similarly, third one I want with respect to the eigenvalue. Okay. Third one, what is eigenvalue? Lambda 3 is equal to 3. With respect to this eigenvalue, what is eigenvector? Okay. Again same story. So a minus lambda I, okay, into x is equal to 0. Directly I am writing. So matrix A, so minus 3. From diagonally you have to subtract 3, right? Okay. Now let us solve this. So it is x2 and x3, and to make it x2 and x3, we have to multiply this equation with 2. So assume this equation is, let us call this equation is big Roman number 1, this is big Roman number 2, and this is big Roman number 3. Okay. So what I am doing is 2 into Roman number 2. So instead of writing like this, I'm multiplying with 2 of second equation. So 2 into second equation, what will get? So minus 2x1. Okay, or simply let us write minus 2 into this. So what will get? Plus 2 into x1 plus 2 into x2, next minus 2 into x3 equal to 0. Okay, and Roman number 1 you take. What will you get? Roman number 1 minus 2x1, okay, minus x2 equal to 0. You club these two, then x1 will disappear, x2, x3 equation in terms of x2, x3 will get already last equation in terms of x2 and x3, then we'll get one of the value. Okay, then what I will do, I'm adding these two. If I add these two equations, adding, then what will get? Let us add. So this is 0, 2x2, so 1x2 will remains 1x2 and minus 2x3 equal to 0, and assume this is new equation, fourth one. So now solve third and fourth one. Solve third one and so third and fourth equation if we solve, then we get one of the value. So from this third and fourth, both the equations are same. So let us take one equation, x2 minus 2x3 equal to 0. So from this, what is x2 value? X2 value is 2 times x3. Okay, 2 times x3. So assume this is number 5. Okay. So look at equation number 1 now. So let us take equation number 1 implies. Take equation number 1. What will get? So minus 2x1 minus 2x1 and minus x2. x2 is how much? 2x3. 2x3. Okay. So is equal to 0. So therefore, what is x1 value now? x1 is equal to minus x3. Okay. x1 is x3. Okay. Minus x3. 2 will cancel out. So now if I assume x3 is equal to, say, look at in this new two equations, fifth one and sixth one, fifth and sixth, common variable is x3. So let us call x3 is equal to some k. Okay. So let x3 is equal to some k, which is from real number system, particularly non-zero real number. Okay. So therefore, what is x1 now? Go back from row number 5. x2 is equal to 2x3. That means 2 times k. x3 value k. Is it 2x3? Check once. x2 is equal to 2x3. Yeah, x2 is equal to 2x3. Fine. So all the values are getting. We got all the values. Then let us find what is the eigenvector. So now x3. So x3 is equal to x1, x2, x3. Okay. And which is, now what is x1? x1 is minus k. Okay. And x2 is 2k. And x3 is k. Okay. If you take k is out, what you will get? Minus 1, 2 and 1. Minus 1, 2, 1. So therefore particularly, so let k is equal to 1. You can take 2 also, you can take minus 1 also, no problem, your wish. Okay. If you take big numbers, calculation become very lengthy. So let us take a small number, it's just 1. Then what is third eigenvector? Which is, if k is 1, we will get minus 1, 2, 1. So this is third eigenvector. So all the eigenvectors we got. Now let us construct matrix P, model matrix, right? So therefore, model matrix P. Now what is P? Indirectly, all these eigenvectors as columns, right? x1, x2, x3. 3 eigenvectors I am taking. Now this is nothing but first one. Let me write all those things. First eigenvector x1. x1 is how much? Again we have to go back. What is x1? Yeah, this is x1, right? Look at x1 is 1, 1, minus 1. 1, 1, minus 1. And x2 is this one, 1, 0, 1. Let me write here. So x1 is 1, 1, minus 1. Okay. And x2 is 1, 0, and 1. Fine. And what is x3? Minus 1, 2, 1. So this is model matrix P. Now let us construct what is n. N is orthogonal matrix now. So therefore, now n is same matrix only, but normalized vectors you take. Because if I find a determinant of n, you should get 1. That is called orthogonal matrix. What is meant by orthogonal matrix? Orthogonal matrix definition is, if A is the orthogonal matrix, then A into A transpose is equal to identity matrix, right? So this condition need to be satisfied. Then that is called orthogonal matrix. Such kind of matrix I need to construct. So once A into A transpose is equal to I, then what is A transpose? Multiply both sides with A inverse, we will get A inverse. Multiply both sides, pre-multiply with A inverse. So A inverse into A identity matrix, A inverse into I, A inverse. So A transpose is equal to A inverse. Indirectly, inverse is nothing but its transpose only. So I need to find a matrix so that it inverse must be its transpose only. Such kind of matrix n I am going to find now. Inverse exists compulsory. Therefore, it should be non-singular matrix. Non-singular matrix means compulsory det is not equal to 0. Det not equal to 0 means compulsory all the rows or columns must be linearly independent. So that is possible in model matrix only. That's why I am constructing first what is the non-singular matrix. So this is a non-singular matrix. After that, I want orthogonal matrix. So this condition need to be satisfied. This condition need to be satisfied means det must be 1. Det must be, how to know det must be 1? Look at A into A transpose is equal to 1. So therefore you apply both sides determinant. Then what will get determinant of identity matrix is 1. Therefore this determinant must be 1. That's why determinant of n must be 1. Okay. Such kind of matrix we need to construct. So let us normalize the vector. So I am finding now normalized vector. So what is normalizing this column vector? 1, 1 minus 1. So we have to divide it with its length, right? What is the length? What is this length? 1 square plus 1 square minus 1 whole square is nothing but root 3. Okay, 1 by root 3. Next, 1 by root 3. We are dividing each component with its length, minus 1 by root 3. Okay, and look at second column, 1 0 1. What is its length? Square root of 1 square plus 0 square plus 1 square. That means square root of 2. You have to divide with root 2. So 1 by root 2, 1 by root 2 and 0 and 1 by root 2. Okay, similarly second one, third column is minus 1 2 1. What is its length? Minus 1 whole square, 2 square, 1 square. So 1 plus 4 5, 5 plus 1 6, root 6. So 1 by root 6 minus 1 by root 6 minus 1 by root 6, and next one 2 by root 6, 2 by root 6, and last one is 1 by root 6. You find the determinant of this matrix, you will get 1 definitely. Check once. Okay, so this is normalized matrix. Normalized matrix of which matrix? Of P, model matrix. So next we are supposed to find n transpose, okay, into the given matrix A into n. N just now we completed, which is normalized matrix of P. So n transpose I want. N transpose means the given matrix n is transpose. So rows interchanged as a columns, right? So first row become first column. So 1 over root 3, 1 over root 2. This is first row. It is becoming first column because we need to find transpose. So minus 1 over root 6. Okay. And second row is becomes second column. So 1 over root 3, 1 over root 3 and 0 and 2 upon root 6. 2 upon root 6. Okay. Next third row become third column. So minus 1 over root 3. Okay. Next 1 over root 2. 1 over root 2. Next 1 over root 6. 1 over root 6. So this is transpose of n. Okay. So next what I want, I have to substitute matrix A, the given matrix A. So which is 1 minus 1 0, right? Next second row minus 1 2 1, right? Third row 0 1 1. So this is the given matrix A, right? Next one, I supposed to substitute the n, the given matrix n. What is n? N is nothing but the given matrix. So here you substitute the matrix n, which is this one. Okay, so this matrix you have to at here. So this is matrix n. So these three matrices you have to multiply. So you supposed to get this matrix cross verify directly. I'm writing. So first row as 0 0 0 you will get. and second row 0 1 0 you will get, and third row 0 0 3 you will get. Okay, you observe the diagonal entries. What kind of diagonal entries you got here? So look at, you got all the eigenvalues which are in the principal diagonal. So therefore all the eigenvalues sitting on the principal diagonal. So this is a cross verification. So then only your calculations are correct. If you are getting all eigenvalues on the diagonal, then your calculations are correct. So call this matrix is sum D. Okay. So the main unknown we computed, which is n transpose A into n. Next we supposed to find out the canonical form, right? So canonical form or simply normal form also correct. Normal form. Canonical form, one more time, is normal form. Okay. So we supposed to find canonical form of the given quadratic form. Okay, canonical form. Yeah. So let's find the canonical form. Yeah, let's find the unknown. What is that? How to find canonical form? According to definition. So y transpose into d into y. This is canonical form, right? By definition. So let's find out this. So y transpose. Okay. And what is d? D just now we computed. What is d? D is nothing but, so this is our d. So d is nothing but n transpose A into n. So n transpose A into n. So n transpose A into n. This is our d. Okay. Into again the given matrix y. Okay. So y is nothing but column matrix, right? So which are 3 by 1 matrix. Let us say y1, y2, y3. Okay. Let us substitute back all these unknowns. So y transpose is row matrix. If y is column matrix, then y transpose is row matrix. So therefore the row matrix is y1. Let's assume it is y1, y2, y3. Three unknowns. Okay. You can take x, y, z also, no issue, but three components you have to take. Okay, what is n transpose A into n? N transpose A into n is nothing but our D, right? What matrix we got? So all the eigenvalues which are on the principal diagonal. So 0, 0, 0, 0, 1, 0, and 0, 0, 3. 0, 0, 3. This is n transpose A into n, or simply D. Okay. And what is y now? Y is a column matrix. Simply y1, y2, and y3. Okay. So multiply these three matrices. So you supposed to get, directly I'm writing, you cross verify once. So y2 square plus 3 into y3 square. This you will get. Check once. Okay. So indirectly here nothing is given means here 0 is given. 0 into y1 square is given. Okay. That means 0 into y1 square. Okay. That means there is no y1. Only y2, y3 terms are there. Okay. So y1, y2, y3 three terms are present. So indirectly the coefficients of y1 square is nothing but this is lambda 1. So this is lambda 1, and coefficient of y2 square nothing is given here, 1. So 1 is lambda 2, and this coefficient of y3 square is 3. So this is lambda 3. So indirectly lambda 1 is equal to 0, and lambda 2 is equals to 1, and lambda 3 is equal to 3. So these are the eigenvalues. So this is a cross verification of your canonical form, whether your canonical form is right or wrong. Over. So next we are supposed to find nature of the canonical form. So what is the nature now? So nature, right? Yeah. So since all the eigenvalues are, what kind of eigenvalues we are having? So all lambda i's are more than or equal to 0. Can I write more than or equal to 0? Because lambda 1 is 0, lambda 2 is 1, lambda 3 is 3. So it's taking 0 also. So therefore finally what I can write is, so therefore the canonical form is, right? So the canonical form is, so I'm writing CF is positive, right? Positive semi-definite. Positive semi-definite. If all the eigenvalues are more than or equal to 0, then the canonical form is positive semi-definite. Next, I suppose to find rank, right? So rank of the canonical form. So what is rank now? So rank is, how to find rank according to definition? So the number of non-zero eigenvalues. What is mean non-zero? Non-zero means negative eigenvalues also will come except 0. Non-zero means so positive and negatives. So number of non-zero eigenvalues. Number of non-zero eigenvalues is nothing but rank. So therefore finally, rank of the canonical form, rank of the canonical form CF. How much rank of canonical form, which is equals to how many non-zero eigenvalues existed here? 1 and 2. So lambda 2 and lambda 3 both, right? So therefore number of non-zero eigenvalues are 2. Therefore rank of the canonical form is 2. Okay. Next one. Index also we supposed to find, right? So index of the canonical form. So therefore index of the canonical form is, so index. So according to definition, what is index now? So number of positive eigenvalues, right? So number of positive eigenvalues. Number of positive eigenvalues. Number of positive eigenvalues. So therefore index of the canonical form is, so index of the canonical form. So CF I am writing, CF abbreviates canonical form. So index of the canonical form, which is equals to positive eigenvalues. Number of positive eigenvalues are how many? 2. So therefore index is 2. Next one is signature, right? So I supposed to find what is signature. Signature of the canonical form. So signature. Signature of the canonical form. So according to definition, what is signature? Difference between, right? So difference between positive eigenvalue and negative eigenvalue, right? Difference between positive eigenvalues and negative eigenvalues. Negative eigenvalues. Okay. So therefore, signature of the quadratic form, right? Signature of the canonical form. How much? So which is, so difference between positive eigenvalues and negative eigenvalues. So positive eigenvalues are how many? 2, which are lambda 2 and lambda 3, both are positive eigenvalues, and negative eigenvalues are 0. There are no negative eigenvalues. Therefore 2 minus 0 is 2. Okay. So that's it. So this is about finding the canonical form of a quadratic form and finding its nature, rank, index, and signature. Okay. And with this, I will end the unit number 2. In the next class, I will start unit number 3, sequence and series.